Hello guys.
The Bluetooth device is ready to pair.
Hello guys.
The Bluetooth device is connected successfully.
Hello guys, welcome back to my YY channel. Okay, let's go back to the discussion of Gibbs free energy and standard change free energy. Okay, but here our focus will be the standard change free energy of chemical reaction. Is I'll show you the formula later, but let's correlate first the sign, whether it is spontaneous, non-spontaneous, like that. I can show you an illustration for that. Okay, so I'm going to illustrate for you. So I have no uh, so, oh my God. So let's do this table. Okay, so that we can understand properly. Okay, like this. We got it. Okay, let's do four squares, and let's level the square one. And then we should correlate the relationship between the enthalpy, and the entropy. Okay, so we have here, let's start with a lesser enthalpy, right? So delta H, okay, is less than zero, something like that. Okay, so we have entropy is equals to greater than zero, and we have enthalpy is greater than zero. Then we have here entropy is less than zero, like this. This is our labeling. Okay, at the top we have change in enthalpy is less than zero, meaning to say negative enthalpy. Then on the vertical here we have the change in enthalpy greater than zero here. This one and this one. And then we have change in enthalpy is greater than zero, meaning positive, right? And then we have the entropy here is less than zero. Zero shot. Yes. Okay. Less than, so this is the entropy is greater than zero here, and this is entropy is less than zero. Okay. So less than zero, meaning to say negative. Okay. Now let's put if the process is spontaneous or let us say non-spontaneous. Okay. For change in enthalpy, which is less than zero or negative, with entropy greater than zero, it is spontaneous or not spontaneous. Okay, how do we know this? Okay, let's solve for the delta G, right? To confirm with that. So delta G is equals to, okay, enthalpy minus the entropy, less than that, okay? So it is understood that the enthalpy is greater than the entropy. Okay, so if it is negative, that means the entropy is uh, lesser, right? Or greater than the enthalpy like this. This is delta G is equals to enthalpy minus this one T this one. Okay. Okay, so since we know that if we have a negative G, delta G negative, okay, let's say negative, okay, this is less than 0, right? Negative, let's say negative 1 lang siya. This equals to delta H. Since delta H here is less than 0, so negative 1. Okay, like that. So, and then minus, let's say the entropy is greater than 0, so positive 1. So it's positive 1. So negative 1 is equals to minus, okay, 1 minus 1, so negative 1 is equals to negative 2. Okay, like this. Substitute only. Delta G is equals to delta H minus T entropy. Okay, let's say negative change in Gibbs free energy. And so we have a negative 2. Delta G is spontaneous. Okay, so this is spontaneous, this one. The first square is spontaneous. I will put spontaneous. Okay. Spontaneous, meaning negative is free energy. When entropy is greater than 0 or positive, and enthalpy is than 0, so spontaneous. Okay. Now, if taking the reverse, if the delta G is energy is positive, so use the equation again here. Okay. Delta G is positive, let's say positive 1. Start with the minimum 1 only. This is the starting point. Or delta G is positive 1. And then correlate that here. Here, because already done here. Already done here also. Okay, so let's say delta H is greater than 0, is positive, right? So positive 1, and entropy is less than 0, is negative. Okay, so positive 1 is equals to 0. Okay, so this one. So positive delta G is substitute values. Delta H is greater than 0 here. Here. Delta H is greater than 0, so understood to be 1. Substitute the positive 1 here. Okay, positive 1 here. Okay, minus delta S. Delta S here is less than 0 man siya. So that is negative. So 1 minus 1 is equals to 0. So if that is 0, that is positive. Okay? Like that. So that is non-spontaneous. Non-spontaneous here and here. This is non-spontaneous. Okay? So for non-spontaneous class, it is positive, gives free energy, is 1. positive free energy. Now, our problem now are the two squares here. Okay, here. Left here. So guess, it is spontaneous or non-spontaneous? Okay, here. Delta H is greater than 0, and delta S also is greater than 0. It is possible we have chemical reaction that enthalpy is greater than 0, positive 1, and we also the entropy is greater than S, greater than 0, positive. Positive both the enthalpy and entropy. It is possible. Okay. It is possible. So let's give an example. Let's draw. I will draw so that we can understand really what's going on. Okay. So it's here. I will draw to understand which is greater delta H positive and delta P greater than 0, and it's in here. This one, we need to fill this empty space here with it spontaneous or non-spontaneous, like that. And here also. So here we have here the, and then here we have the greater than 0, also the entropy here and here. And the other one is greater than 0. No, here, less than 0 here, and greater than 0. So both the same directly proportional, the H and the S. So the entropy is greater than 0 and the enthalpy is greater than 0. So we need to supply here with this is spontaneous or not. Here also, here in the empty space, we have greater than 0 and greater than 0 also. Okay, less than shot. Okay, less than 0 and less than 0 both here. Okay, so we need to supply here spontaneous and spontaneous, spontaneous and spontaneous like that. So in order to understand properly, we need to consider the substance water as our basis. Okay, so like that. So water, we have the water will undergo the freezing point of 0 degrees Celsius, something like that. Okay. So I will draw a flask. So how can I draw the flask? I forgot. Like this. Is it a flask? This is an ice. This is also the liquid water. Okay. This one. Consider this one. Ice, which is water in a solid phase, a freezing point of temperature 0 degrees Celsius. So if 0 degrees Celsius, that will mean 42 degrees Fahrenheit. Am I correct? Okay. So if you have Celsius to Fahrenheit, the value of 0 degrees Celsius is 32. Okay. I guess so. Try to convert that one also. Okay, so let's use Celsius na lang siya so that we don't want to prove that it is 32 degrees Fahrenheit. I think it's the same. 32 degrees Fahrenheit and 0 degrees Celsius freezing point of water, ice is just the same. So like this. T is equals to 0 degrees Celsius. Okay. Or it could be 32 degrees Fahrenheit. Or it could be in 273 Kelvin. Check, guys, if it is correct. The freezing point of ice, liquid turns into solid, and the temperature is 0 degrees Celsius, and then 32 degrees Fahrenheit, and the Kelvin is 273. Okay? Correct me if I'm wrong. So maybe I forgot. It's due to the computation if we are down, but it's not just have like that. Okay? And then for liquid water, the boiling point is 100 degrees Celsius. Okay, 100 degrees Celsius. Okay, so in terms of degrees Fahrenheit, that is 212 degrees Fahrenheit. I think so. This convert by your own. 100 degrees Celsius is how many degrees Fahrenheit? I think 212. Okay, and in terms of Kelvin, we have 373, right? Kelvin. So these are the 3 units of temperatures equivalent for the ice freezing point and for the boiling point 100 degrees Celsius. 3 values in degrees Celsius, Fahrenheit, and Kelvin respectively. Okay. So if you are out, then use the formula of degrees Fahrenheit is equals to 9/5 times degrees Celsius plus 32, or 1.8 times degrees Celsius plus 32. Okay, and use also the degrees Celsius formula, which is 5/9 times degrees Fahrenheit minus 32. Okay, like that. Okay, use that one. So, and the Kelvin is very easy. Okay, degrees Celsius plus 30, like your shot. Okay, like that. So runtime, I think it is 1.8 Kelvin. 1.8 times Kelvin. Runtime, degrees runtime. But that's not important too much. It's enough for 3 units of temperatures, right? Okay. Now, we need to discover the spontaneity of the ice and the liquid water. Okay. Originally, plus let's say this is liquid water at its boiling point. For example, this is the vapor is vaporizing into the atmosphere like this, assuming only it's one. Okay, the liquid water is evaporating. Okay, in the first place, after boiling this one, you put in the table, for example, matcha, and then it vaporizes into the atmosphere. Okay, okay. Because in the first place, there is also natural volatility or escape to the atmosphere, but not that too much. It will still vaporize, something like that. Okay, but very slow. Okay, I think so. But if it is boiled, so the more vapor will escape to the atmosphere from this flask. Okay, this is originally having a high temperature. Okay, so if it is a high temperature, so there will be a heat transfer from liquid water to ice. Okay, because the thermodynamics in the second law, the heat flow or heat transfer is from higher temperature to the lower temperature. So the higher temperature is 100 degrees Celsius with water that starts to vaporizing. Then it will transfer to the ice. Because ice has a lower temperature, it's very cold, freezing up. Okay? So the heat transfer will be there. So it is heat released from the liquid water. Okay? But heat absorbed by the ice. Understand? Okay. Like this. So the arrow will be like this for the heat energy transfer. Like this. Heat energy transfer, let's say T release ng siya is gonna be TR lang para dali. Okay, temperature release na siya sa TR. Or shall we say QR, right? Because heat is Q ng siya. So heat released is equal to the temperature release, which is originally hotter, which is 100 degrees Celsius, will transfer to the ice. Okay, and now the temperature of the ice will become hotter, starts to be hotter already. Okay, so this is 0 degrees Celsius here, right? So the transfer from high temperature man, so from hot environment to cold environment. So this is the second thermodynamic shock. Okay, so it's gonna be like that. So our problem here is to determine the spontaneity of the process to fill this gap here and here. Okay, how can we relate this? So we have the enthalpy, right? Enthalpy, so we come to think the relationship between the enthalpy and the heat. Okay, so if we try, I found difficulty, guys, because I don't prepare for this. Okay, I'll just have the topic and then I'll just come to our relationship, but I don't really, prepare what's the relationship, just on the spot. Okay, so wait. Let's pause for a second. Okay, okay. Enthalpy, this is the heat content, right? Heat energy transfer. So this will be directly proportional to the Q, which is also the heat released. Now, if you release the heat here, the temperature will be a little bit lower. So it will have a negative, starts to become negative heat, right? So this is starts to be negative heat. So that's gonna be negative enthalpy in the liquid water, right? So negative enthalpy. Okay, so negative enthalpy siya, okay, and is less than 0. So negative enthalpy siya. 3 ang liquid ice here. Okay? Because the temperature will become lower na siya to be transferred to the ice. And the ice will become hotter. Because the principle, second law of thermodynamics, the heat transfer will be from higher temperature to lower temperature. So the heat or the enthalpy of the liquid water will become lesser now. So this follows that enthalpy is less than 0 na siya. So less than 0, it could be negative or anything that is lesser than 0 or negative talaga siya. So expected it to be ang liquid water. I will put the liquid water here. Liquid water. Okay? Liquid water. So, liquid water now. So here. So, the other one, the ice, the temperature of the ice will become higher. Ice will absorb the heat coming from the liquid water. So the enthalpy, which is directly proportional to the heat, so that is rising temperature, rising enthalpy. We'll put here the ice in this space. Ice. Okay, here, ice. We need to determine the process of the ice and the liquid water, whether it is spontaneous or not. Okay, now if we put the ice here, delta H is less than 0, which is negative. What is our entropy here? Ice. Our entropy is greater than 0. So if our entropy is greater than 0, that is positive 1. Now substitute now in the delta G equation so that we can determine if it is spontaneous or not. Actually, we have only an idea. If the entropy will increase, it will cause irreversibility of the process. So if that is irreversibility of the process, it's gonna be non-spontaneous. I don't know, but let's just substitute first. Okay, for the formula. So if we have the formula, delta G is equals to enthalpy. Hirap, no? T times delta S, second law of thermodynamics. Let's substitute that here. Our enthalpy is Here, for the ice, muna ha, let's determine if it's spontaneous or not spontaneous. We cannot do magic, though we have an idea, but maybe it's wrong. Okay, so enthalpy is greater than 0. So it could be positive 1 lang din siya. Mag-start as a positive 1. Okay, so to substitute that here, the enthalpy for the ice, positive 1. Minus, and then the entropy will be here. This is entropy is greater also than 0, so it's positive 1. So positive 1 minus positive 1, like this. So this is 0. So if that is 0, that is not negative, right? So if that is not negative, so that is non-spontaneous. Nakakaloka. So, non-spontaneous siya at 0 man siya. Okay. Kung siya o non-spontaneous man yun siya, increases man the irreversibility if the entropy will increase. So, increases the irreversibility. Dili na yun siya reversible reaction. But take note, reversible reaction is spontaneous reaction. Okay, so irreversible reaction is non-spontaneous. So this will be non-spontaneous at high temperature because the ice will absorb the heat coming from the liquid water, which boiled a while ago. So it absorbs heat. So this is non-spontaneous at higher temperature on ice. So non-spontaneous at higher temperature, higher up, okay? Okay, now for the liquid water. So we have an idea already that it's gonna be the reverse, right? For this, but let's just substitute in the formula. Okay, liquid water, our enthalpy is greater than 0. O less than, dahil siya garaman siya. Hindi po so pag-explain if there's no whiteboard. So delta H is less than 0, so it could be negative na siya. For example, substitute in the here, second law of thermodynamics. So delta G is equals to delta H, limon ka na negative. So negative K, less than na siya sa 0. Mag-start lang dito sa 1, okay? Negative 1 minus, let's say the entropy here will be here, because it's here man siya. The entropy will be also less than 0, it's negative 1. So negative 1 minus negative 1. Ay, chagawa. Negative 1 plus negative 1 is negative 2 on delta G. Wow! So if this is a negative 2 delta G, this is spontaneous. Okay? I told you the reverse of non-spontaneous for ice. So spontaneous. So this is spontaneous at, since liquid water are releasing the heat to be transferred to the ice, so at lower temperature. So spontaneous at lower temperature. Okay? Like that. So solve na tayo. Okay, this is the relationship now. So the ice will be non-spontaneous reaction at higher temperature when enthalpy greater than 0 and entropy greater than 0 also. In proportion of what the enthalpy and the entropy. And for the liquid water, it is spontaneous at lower temperature, okay, and at the same time at less than 0 entropy and less than also enthalpy. Ganun lang siya pag-memorize, guys. So ice, okay, less than ang enthalpy, less than also the entropy, directly proportional. So ice talaga siya. So spontaneous, negative ng enthalpy. So at lower temperature, yes, lower temperature siya. Okay? Ganon, di ba? Okay. Tama ba? Again, liquid water, di-transfer niya ang heat. So, atong usbon ha, liquid water will release the heat. So, sa ito pa siya higher, sorry, see? It is lower temperature, i-release na niya ang heat. So, not spontaneous at lower temperature. Sorry. So, originally, high temperature siya. And the heat energy is being transferred man siya. So, gradually decreases the temperature. So, it's non-spontaneous at lower temperature ang ice. Tama, uy. Ice mo na yung bibigyan. Nakakaloka. Sakto. Sakto siya. Okay? Nalipan mo. Ice matay siya din. Okay, sakto siya. Sakto siya. Sorry! So, karoon valid, ice, the temperature will be increasing because it absorbs heat and temperature of liquid water. Okay? So, increasing a temperature, that's spontaneous, because it has a capacity value of Gibbs free energy, the second of thermodynamics. Okay? So, this one. So, taas or higher enthalpy greater than 0 and permanent. Okay? Like that. And then for the liquid water, we have spontaneous at lower temperature because it is its heat. The heat of the liquid water has been released and transferred to the ice shock. So the temperature is slowly lesser, reducing, and also the heat. So meaning to say, non-spontaneous siya, ay paano siya, at lesser entropy less than 0, which is -1. Okay, and also the enthalpy is less than 0 also. So ganun lang siya, try to determine. So this principle will be answered, then you can say, oh my God, this is wrong because this is not spontaneous like that. So it deviates this principle. Okay, this is the purpose of the theory for that. Okay, we can say after the problem solving. Okay, like that. So our example really here is the ice and the water. The very, very basic example of heat transfer or heat energy transferred from hotter environment to colder environment, or from high temperature to lower temperature. So that could be the temperature gradient or differences from final to initial, something like that. Okay? That's enthalpy naman siya. Because transfer man siya. Okay? So muna na siya. And then, so if we try to put also in another situation, for example lang this sounds to be hypothetical, right? So for example, if we have a cliff, and there's a cliff, and then let's try to draw again, so that we can really understand, right? Illustration first, concept and theory. Okay, like this. So how can I do this? Okay. Another thing is, if we have a cliff, guys, okay, then like this, the cliff will be like this. Okay. This is a cliff, like this. Okay, cliff here, and a cliff here also. And you throw a ball from here to, let's say, a ping pong ball or soccer ball or whatever. Okay. The ball, guys, will keep on bouncing back and forth. The ball will continue, bouncing back and forth. Okay, this. Okay, so no need to add internal energy for this. Okay, it has its own internal energy to keep on bouncing back and forth here. Okay, like that. Whereas if there's another cliff that is not like that only, and we have a plane here, and you let the ball going up here, like this. If there is, here's another ball, there's a cliff here, and there's a surface here, ground. You need internal energy to push the ball going up to the cliff. So, this is an example of non-spontaneous. This one. This is an example of non-spontaneous. Meaning this is not a reversible process because you need internal energy to push this ball in going up to the cliff. And the first illustration, we don't need illustration. We don't need to push the ball on the other side of the cliff because if you throw that downward, it will keep on bouncing back and forth. There is its own internal energy. No need to add internal energy. Okay? Until such time, the internal energy will become zero. Okay? If it is equal to zero, and that is the time also the work done of the ball stop. Because there's no distance covered anymore. Vertical distance covered anymore because it stops somewhere out in the shaft. Okay? So time will come that the work will be equal to zero when the internal energy is equal to zero also, right? Because no external force can apply here. But here, we need force applied to push the ball up. So we need internal energy, extra more internal energy to push it into the cliff. Okay, so this is a non-spontaneous such it will go to the equilibrium stage. When the ball stops in the center here, okay, there's no motion anymore. So it is now in equilibrium. If it is an equilibrium, guys, the Gibbs free energy is equal to zero. The internal energy is equal to zero. And the process. So your Gibbs free energy is not equal to zero. Okay? You get the point? Your Gibbs free energy is not equal to zero. Okay? So in fact, you add internal energy which is positive. Okay, so understood your Gibbs free energy also will be positive. So non-spontaneous na talaga siya. So irreversible. Okay? So, in this manner, guys, so it increases the entropy because it is positive. Positive is non-spontaneous. If the Gibbs free energy is positive, increases the Gibbs free energy and also the entropy. Okay, like that. Okay? Directly proportional with each other. So the more it is random and disorder in the second illustration. Okay, here. Because you keep on pushing something like that, or to go up. Okay, here it's just natural process. Okay? You will put that here, it will slide down and back and forth, back and forth. No need to push by artificial force of a person. Okay, purely dropping through gravity. Here. Okay, a lot of when it stops, the motion is zero, the velocity is zero, the Gibbs free energy is equal to zero, like this, the entropy is equal to zero, and then the reversible process. Okay, and here the reverse for the first illustration. Okay, like that. We need more internal energy, which is a positive internal energy to push the volume going up here. Wala nga namang negative. So positive talaga siya because you exerted that on the system. Remember, work exerted on the system is positive value. Okay, it will be connected there also. Work done by the system is negative. So this is on the system siya. The system here is the cliff and the ball. Okay, something like, the cliff is the surrounding, the ball is the system. Sorry. Okay, like that. It's always the system, and so the system here is the cliff, and the ball is the system, and the cliff is the surrounding. Okay, it's gonna be like that. Always surrounding system. Okay, like that. It's very clear, ha? So mag-solve na ta. Ano pa dyan yung isa? I need to discuss the reaction formula for if we have the Gibbs free energy na wala is zero at the top. Like a degree. So if there's a degree at the top of the capital G, delta G that is standard Gibbs free energy, we have also another, this is delta G with a degree symbol at the top, and then reaction subscript. So delta G, means at the top, small circle at the top, and then RXN. RXN meaning reaction, the abbreviation of reaction. If you can find that in the medicine, the labeling of the medicine of the carton, especially the syrup is what are your medicines. Okay, you go to the pharmacy, buy a syrup bottle, and it's in the packaging. There's a word RXN. That means reaction. Okay, RXN. So it's just the same like that. So delta G RXN. So we'll put. Okay, that's the abbreviation of reaction. Huh? RXN. Put that in your brain cells. Okay, like that. So Gibbs standard free change of the reaction of that. Ganun siya. This one, RXN. Okay. Delta G with small circle at the top, RXN is the change free energy standard. For standard, if we have hydrogen gas plus, let's say, hydrogen gas, Haber process for the production of plus H2 gas is equals to ammonia, right? The raw materials for the production of fertilizers. Okay, so NH3 balance the chemical reaction. It's easy to balance like this one, N2 plus H2 equals H3, right? So, i-show na ako because I've already discussed this in my previous how to balance the chemical equation. I'll just try to make this direct. Okay, like this, blah, 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 so on and so forth. So, okay, like this. Okay. I make it direct because I don't need to explain more about the balancing of the equation because you have if we have the data for that standard, let's say proceed product, because it's the final stage, right? What is the product final minus definition or product minus balance? Okay. Number of moles of the product, and you have to do it, and you have to do it individually. For example, if there are 3 products, then do it 1, 2, 3. Indeed, break that individually. Okay? If there's only 1 product, then usa lang siya. 1. Okay, ganun siya. But the summation magod siya. So number of moles of the product times the total enthalpy of the product. Okay, minus the summation of the number of moles of the reactant, and then the change of enthalpy of the reactant, something like that. If the problem will ask you, calculate the standard change of free energy, no need to argue. It means that it is in equilibrium because the delta G will be 0 in a reversible reaction. I have to put 2 arrows here now. Okay, like this. 2 arrows na siya. See? So this is going to the right, going to the left 2 arrows. That means reversible reaction. Delta G is equal to 0 or get. You're going to say standard change free energy of the reaction is equal to the summation of the number of moles of the product times the delta change of the enthalpy of the products minus the summation of the number of moles of the reactants, okay, times the delta change in the enthalpy of the reactants. Now, enthalpy, guys, and entropy will be directly proportional with each other. So you can also use the standard change free energy of the reaction is equal to summation of the number of moles of the product times the delta change in the entropy na siya minus the summation of the number of moles of the reactants times the summation of the change of the entropy. Okay, so this summation of the number of moles of the enthalpy change, or let's say entropy change of the number of moles, this is what we call the formation, the enthalpy formation of the reactant. Summation of enthalpy formation of the reactants and the products. Okay, and entropy formation of the products and reactants. Okay, formation, the term formation, don't forget. Okay, something like that. But anyhow, you can understand through the problems also. Okay. We can use this one, But guys, it will not mention calculate the standard change free energy. Do not use this one, because this is only standard. The word standard signifies this delta G with 0 up. Because in the problem also, in the actual examination, they don't put the G with 0. It's only word. You know the keypad in the computer, the laptop, it's very difficult to put 0 at the top of the letter. That's why the problem solving, we just say, calculate the standard change free of energy, but the question will not put the delta G and the Z small letter, small 0 at the top, because it's very difficult to encode that in the computer. You understand my point? You need to shift like that. Okay, just like the NE. The NE is very difficult to put in the encode in the presentation of the problems. There's a lot of like that, and that's why they make it a word. Calculate the standard change free energy. So that means delta G 0 like this. Okay, they cannot show that. They cannot show the delta G because there's no small letter 0 at the top. It's very easy to encode in the laptop or in the computer during the typing back sa question. Okay, so there's also limitation, something like that. Okay, so just like an NE, sometimes very difficult to put that in the, okay? So you know what I mean, in the keypad. Okay, sometimes. So that's why they don't put the symbol with small letter at the top of the standard change free energy. They will just say, calculate the standard change of free energy. Let's use this equation. Now, if the question will only calculate the Gibbs free energy or the free energy only without the word standard, then use the delta G only. Okay? Like that. Ang atong identification will be the word standard. That matters a lot in the question. Okay? If given the chemical reaction, then calculate the standard change of energy. Use this formula. Okay, but it doesn't state like that. Calculate the free energy lang siya, so you opted to use the Gibbs free energy. Okay, even though the word Gibbs is not stated, only like that. Calculate the free energy. Understood naman na siya ng Gibbs free energy na siya. Okay? You understand? That's also delta G, even though the word GIBBS is not mentioned in the problem. Sometimes like that only. Calculate the free energy of the chemical reaction. That means Gibbs free energy delta G. Doesn't mean that you have to put Gibbs to understand that it's delta capital G. It's not like that. That's very literal. Okay, it's word for word. Sometimes the problem is stated to be like that. Okay, but sometimes also have put Gibbs. But sometimes no need to put Gibbs in the problem solving. Okay, so that's to be honest. Okay, and then this change in standard, there is always standard. If there's no standard, they do not use this one. Alas. Okay? Like that. Okay, there's also another equation for this of okay. If we treat the delta G in equilibrium, okay. If it is not involved in a chemical reaction, we have delta G is equal to delta change standard free energy like this. But this is not a reaction. This is only individual. Something like this equals to R, P, L, N, Q. This one. Like this. There's also a formula like this, guys. Okay. Listen carefully. Delta G is equals to the standard change in free energy plus universal gas constant R times the capital T in Kelvin times L and Q. Now, we treat delta G equal to T. That's the time equilibrium constant will appear now. So the Q will be lost. It replaces with K na siya. Equilibrium constant, K. Okay, remember that in this manner only that involves changing free energy. So I don't have to derive now because it can be derived, but it takes a long time. Why the Q will become K alone. You don't have to derive na, okay? So memorize na lang din siya. That's the only way. So calculate the Gibbs free energy, and ganun siya, and then there's a time, and then there's a hit that you can compute. But if you ask for the equilibrium constant, then substitute the Q with K. So it will turn out that the equation will be delta G is equals to the standard change in free energy plus RT Ln times K na siya. Replace Q with K. This will be happening, guys, in reversible reaction when delta G is equals to 0. So it will be simplified our formula into delta G standard change in free energy is equal to negative RT Ln K. Muna ni siya. Muna gini siya per me. Okay, the simplified formula for the standard change in free energy simplified into negative RT Ln K. K is the equilibrium constant. Okay, now we have also the correlation for that. Okay, if we have change in standard change in free energy which is less than 0, so we have a greater K above positive 1. Okay, we'll just put that in correlation. Okay, so importante mo gud ang theory. Okay, like this. Okay. As I told you, I will never pass the board examination if my theory is very less. I build more on the theory and the concepts and principles, though I'm not that, expert or very good in problem solving. Average lang po ana, okay? But dili jud ko ni develop sa theory, concepts and principles through comprehension, okay, and memorization, analysis for the facts, principles, concepts like that, basic concepts, okay? Because not all problem solving will come out in the board examination, okay? Like this. Or any examinations in the future examinations if you are students right now. So not limited only to board examination, right? Okay. So, asa naman to? Okay. Ganon. So, negative RT Ln K. Ganun siya. We take note, guys. If you don't see the arrows going there to the right and going to the left, that is not reversible, ha? Okay, then do not apply this formula, this one. Do not apply this, because this is only for delta G is equals to 0 at equilibrium or reversible reaction. Okay? Okay, you got the point? Now, so the relationship between the equilibrium and so if the standard change of free energy is less than 0, then our equilibrium constant K is greater than 1. This one. Our K is greater than 1, so our chemical reaction will favor to the products. Just like in Chatellier's principle, remember that one in chemistry? We have whenever a stress is applied to a system of equilibrium, the equilibrium will shift in such a way to reduce the stress. The stress there will be the pressure, the temperature, the volume, the number of moles. And then if you add the number of moles, what will happen? It will shift to the right, it will shift to the left, it will shift to the reactants. The principle is just like that here. If you remember the Chatellier's principle on theory in chemistry. That's why I told you build the theory first. Okay, like that. Okay, so just like the principle here. Okay, so if the change in standard change in free energy is less than 0, our equilibrium constant will be greater than 1. Okay, so the chemical reaction favored the products. Okay, and then the reverse will hold through if the standard change our K is less than 1. Okay, meaning negative values. For example, 1 times 10 to the negative 2, Okay, 2 times 10 to the negative 3. Ang exponents negative, so bingo, that is, less than 1 ang K. Ganun siya. So, the chemical reaction favored to the reactant. So that's theory, right? Like that. So sometimes the question is like, what will happen to the chemical reaction if K is less than 1? Then you have K, then I will shift to the right, shift to the left. Okay, you have to analyze and then you can answer. Okay, statement only, a statement question. So which is true, which is false, which is not a true statement, which of the following is not a true statement. For example, the chi is positive, spontaneous. Okay, this is the purpose of this explaining for the student. This will come from the theory questions in the examination. This is the purpose really. Okay, like that. Okay, now if you are not balanced, you only focus on the problem solving, though majority will pass, but there's still a chance that some will fail. Okay, because there's theory in the examination. Okay, in fact, there's more theory, I think so. Because I consider theory also the problem that is very short. Short only, direct substitution, like that. I will not consider that as a problem solving. Because sometimes there's also questions like that. For example, if the heat in the board examination, I consider that as a theory. Okay, I will never consider that as a problem solving. The one I considered problem solving is really a 20 paragraph and so many required. That's problem solving for me. But if direct substitution only and I can get the answer, that's theory for me. Okay. Okay, so there's also a lot like that plus the theory. Okay, that's why it builds my scores in passing because of that. Okay, so build more on the theory, concepts, principles than problem solving. But do not focus on the difficult and complex problem solving. Especially unit operations, very tempting. Unit operation, heat transfer, okay, distillation, flotation, okay, sedimentation, leaching, drying, like that, crystallization. Okay, very tempting really. You focus on the difficult problems and you will lose the theory and concepts, which is more important. Okay, because in real world, you don't have to go to the complex process really. Okay, you have to start with a core foundation so that you can really understand. Okay, something like that. Okay, it will not be applied in the real world also too much. You have to integrate, you have to differentiate like that. Okay. Because in unit operations and unit processes involves also sometimes integral calculus, differential calculus, and differential equation. But it will never use in real world except for design stage. Okay, design. Okay, engineering design of circuit plant, engineering design of circuit equipment, machineries, or whatever included there. Not on the actual process. We don't have to integrate there. Oh my gosh. Okay, like only algebra, a little bit of geometry and analytic geometry. But trigonometry, right? But very small only. Usually the right triangle, the Pythagorean theory always applied, especially in the computation of the elbow pipeline, the angle of inclination for the connection of the parts, and you have to compute for the T, elbow, the run shot, what is the angle of inclination. That's the time you use the Pythagorean theory for that. That could be applied for the piping type of job, or especially piping fabrication. I am not mechanical engineer, but I understand that you'll use that most of the time. Angle of inclination, Pythagorean theory, and like blah blah blah, so on. So that's the time you will use tangent theta is equals to the base over the okay, the base over the height. Okay, cosine theta, ganun siya. Base over the hypotenuse. Sine theta, okay, the height over the hypotenuse. So hypotenuse is this pipeline, outer diameter, inside diameter. Okay, circumference to pi r squared, siya. Okay, then pi d squared over 4 or pi r squared lang siya. Because diameter is equal to 2r, then it will result to pi r squared is the area, or pi squared over 4, something. And it will go also to the volume of the sphere. Okay, 4/3 pi r cubed, maganda lang siya. Okay, the basic. And then the area of the rhombus. I think rhombus wala applicable in the real world na. Rhombus, trapezoid, hindi siya ma-apply. What applies ka na lang mga simple na shapes? Round, circle, rectangle. In fact, oblong will not be applied also. Oblong. Most of the time in real world, when you are working, always the rectangle, the square, the cylindrical shape, the circle shape, the round shape. It's always like that. And coupled with basic mathematics, algebra, and trigonometry. That's it, bingo. No need to go to the calculus. If you want to make yourself complicated, then use it. No. But if you try to compare the three methods of solving mathematical problems, I would rather go to the most basic one, which is the algebra. Why should I complicate to integrate, to differentiate? In fact, we will get the same answer in the real world, okay, of working. In school, no problem. Okay, in university, institution, because we have to maintain grades in order for us to pass the subjects, right? But what I mean, applicability in the real situation, okay, no longer needed really those kind of subjects, except for the engineering design stage. In designing, for example, pump, motor pump, something like that. Okay, in this chemical reactor, what else? In plant design or equipment design, so it's needed there. Integral calculus, differential calculus, differential equations, and even I think advanced engineering mathematics will also be applied a little bit. Yung mga Laplace equation, because they remember that advanced engineering mathematics using Laplace equations. Okay, then you try to mix it with differential equations and okay, we will go that. Okay, so that's it. No, really not powerful problem solving. I discussed this gives me energy because that's standard which is energy, because this is also related to the second law of thermodynamics. Actually, we are still in the thermodynamics part. We are not in the physical chemistry. Okay, we are still in the thermodynamics. Some of the topics in physical chemistry will be connected also in thermodynamics if you can feel it, if you can remember it. Okay, so there's a little bit of mixture. Something. In fact, also in chemical calculations, stoichiometry, sometimes also requiring the heat, okay? The heat absorbed, the heat released in your chemical reaction, even though in chemical calculations, not really in thermodynamics, it goes like that, it's a continuous process, the applicability will be interconnected with each other, something like that, okay? So that's why it's being mixed. Okay, during the examination. Sometimes we will be confused, right? So to those who can relate, we will be confused with it's being mixed already. Oh my gosh, okay? And sometimes, how can I do this? I can use the transfer for this, I can do like this. And sometimes, by just thinking alone, sometimes it will consume your time for just one number. Because you are, I'm telling you the real story, taking the word examination. Sometimes you will be confused what really the appropriate equation for, because you have so many formulas in your mind. And then, is the one, is this, because it's still the same. So you try to the first formula, second formula, which that produces the choices there. And then you can get the answer. Something. Nakakaloka talaga, no? Okay. Okay. But I love it. Theory talaga. Okay. Theory, principles, and concepts. I love it. Okay. So ako naka-focus. Charot! Okay. So now we go to the. It doesn't really focus on the problem. So I'll just go to the not too difficult one. Only to the easy. average, a little bit above average, but not that difficult. If that is very difficult, I will never go, and I will just solve the not difficult. Okay? And it's very tired. Became tired of thinking. Okay? Of the complex of the problem. There's a lot of complex problems really in chemical engineering. Sometimes you cannot really understand. My gosh. Because I think my IQ is not very high, maybe I cannot understand. But if you will try really to buwis buhay, I think I can learn this also. Maybe I don't have the courage to dig deeper for those complex problem solving. Okay? Okay. Now, thank you so much for watching. If you like this discussion of the theory and concepts of second law of thermodynamics in relation to the Gibbs free energy, the standard changing free energy, and to be the enthalpy, blah, blah, blah. So it's your option if you do it. It's up to you. It's your option if you do it or not. Okay. Again, this is Engineer Sotero. Again, this is Engineer Sotero, who's an engineer, chemical engineering graduate of Cebu Institute of Technology University, and presently an occupational safety shop engineer. Bye-bye, and with everyone.